Okay, so in this lesson, we're going to review a lot of the information about functions. And I do think most of this will be reviewed for you, but I just want to hit the high spots on some of these, and then we'll get to the part that really has to do with our lesson, which is the domain and the range, and restrictions on the domain. So, first of all, when you learned about functions back in Algebra 1, they gave a long definition, which is here. It's a correspondence which assigns each member of the domain to exactly one member of the range. But in short, what we determined was that the x's do not repeat. X values do not repeat. So if you have a list of ordered pairs, it's really easy to see. If you had 2, 3, and 2, 4 in the same graph, then that graph would not be a function, because a function, the x values do not repeat. Also in a function, there is a relationship between the independent and the dependent variable. The independent is sometimes called the cause, the dependent the effect. The independent is usually considered x, the dependent y. Of course, we could use other letters, but they're really the input and the output. The x value is what you input into the equation, like here, and then what you get out of it is your y value, or the dependent variable. Y depends on x. Y is dependent upon what you put in for x. Y depends on x. Now also, along with that, we have some different terms that we do talk about with functions. Any set of ordered pairs that I can graph, even if that set of ordered pairs is not a function, it can still be graphed and called a relation. So any set of ordered pairs is a relation. It has to be specific to be a function, because with a function, the x's don't repeat. The domain are all of your x values. Your range are all of your y values. And so we're going to talk today a little bit about how we describe the domain and range. Also, functions have zeros or roots. Those are also sometimes called the x-intercepts of the graph. And sometimes we call them solutions because they are the places where the function is equal to 0. The y value is equal to 0, where they cross the x-axis. And so many times you'll see the word solutions to describe them. But remember that all those kind of mean the same thing: roots, zeros, x-intercepts, solutions. All the places where the graph crosses the x-axis. All right, then we also have function notation, which we were using in our last unit. F of the independent variable, which is usually x, is equivalent to the dependent variable, which is y. And so this relationship here, this function notation, is why many times we interchange f of x and y. F of x is equivalent to y. Now to the part that really has to do with what we're doing today, and that is restrictions on the domain. So we want to talk about how we could describe the domain of a graph or the domain of a function. And there are really only a couple of situations, types of equations, functions that you're familiar with that have restrictions on the domain. The first one would be an equation that has a denominator, or a fraction, which is called a rational function. So you'll hear me talk about rational functions later on in the year again. But a rational function, or a function that looks like a fraction, is going to have a restricted domain because the denominator in that function cannot equal 0. And the reason for that is because you cannot divide by 0. It's not defined. You cannot take any number and divide it by 0. You can't do it. So it's not equal to anything. It doesn't exist. So let's talk about that for a minute. If I were going to try to explain this, when you're dividing by a number, let's just say I have one pizza and I'm going to divide it by 2. I'm going to split it in half. Well, then I get 2 pieces. So I can divide one thing into lots of pieces, but I can't take that one thing and divide it by nothing and make it disappear. It doesn't happen. So you cannot divide by 0. And I'm making a big deal about that because this comes up all year long, this 1 divided by 0 thing. It is not defined. You can't do it. So I'm going to go ahead and go down here to this first example here. I want to talk about how that's going to work for us. So what we want to do here is make sure that this denominator never equals 0. So I'm going to take that denominator. It does not make any difference. The numerator is irrelevant. Just the denominator, and set it equal to 0. And then I'm going to solve that. And to solve it, we need to factor it because it's a squared term. So like the lesson that we had before, this one is a difference of squares. X times x, 1 times 1. We want the middle term to go away, so 1 plus, 1 minus. And then I can set these factors each equal to 0 because this number, whatever that number is, times this number, whatever that number is, when multiplied together, give me 0. And the only way that can happen is if one of these is 0. So I'm going to set x plus 1 equal to 0 and x minus 1 equal to 0. And then I get subtract 1, x equals negative 1. Here add 1, x equals positive 1. So what I know now is that if I were to put either of these values in for x, it's going to make this function equal 0. 1 squared minus 1 is 0. Negative 1 squared is 1, minus 1 is 0. So in my domain, I know that x cannot equal plus or minus 1. But it could be anything else. So we could write this just like that, except you might want to put in front of it, the domain is all real numbers except, this is with the exception, that x cannot equal plus or minus 1. Now, this is a portion of set notation. There's really a little more to it than that, but this would work. This would be a description of our domain, but I'm also going to show you interval notation. And I'm not sure if you guys did this last year or not, so it could be new. But when we're looking at this solution on the number line, and we said that x cannot equal negative 1, it cannot equal positive 1, but it could be anything else, then I could put some open circles there, and then I'm just saying that anything else, any other real number, would be okay to put into that function. In interval notation, you kind of describe this situation from the left to the right. So this arrow just keeps going to the left, and if I keep going in a negative direction, that's negative infinity. So I start this with negative infinity, and then I have to stop at negative 1 because negative 1 doesn't work. And then in between here, I have a little set from negative 1 to 1. And then over here on the right, I go from 1 to infinity. And this is called interval notation. So we're going to practice using interval notation. This is the way I'd like for you guys to write your answers. Now, if you are not sure about this and you just want to, write the domain however you can state it, as long as it is clearly correct, I will take it for now. But this is what we need to be headed towards, interval notation.